In this section, we're going to see if we can build on the idea that the definite integral tells us net area bound by our function and the x-axis. So we're going to see if we can use the definite integral to find the area between two curves. So if I have some curve, perhaps it looks like this, and then another curve down here, can I find the area in between those two curves using definite integrals? It turns out that the answer is yes, we can, and it's a very logical process, I think. So let's just jump right in. But before we do that, I want to do just a little bit of review. I would like to find the area between the graph of f of x equals 2x minus x squared and the x-axis over the interval 0 to 2. So here I've sketched in and kind of shaded the area that I'm looking for. This red function, that is my function f of x. And I think that having a picture for all of these problems is going to be very, very helpful so that we can see exactly what the area that we're trying to calculate is. Because if we have any intersections between your function and, say, in this case, the x-axis, then we would need to break that integral up into two parts. Here, I only intersect at 0 and at 2, so I can do this, I can actually find this area using only one integral. If I had intersected, let's say here at 1, I would have to split this integral up into two separate definite integrals. But for now, I can just find the definite integral from 0 to 2 of 2x minus x squared dx, because I know that the definite integral, this guy right here, tells me the area bound by the function, which is this red line f of x, that's this guy right here, and the x-axis. So I'm just using what I already know, what we talked about in the last section. So let's evaluate this definite integral. First, I need to find my antiderivative. I should have x squared minus x cubed over 3, and I'd like to evaluate this at 2 and at 0. So let's see, I need 2 squared minus 2 to the third over 3 minus 0 squared minus 0 to the third over 3. For that second term, 0 squared, well, that's just going to be 0. 0 to the third is 0 divided by 3. That is also going to be 0. So those two terms are just going to drop off. 2 squared, that should give me 4. Minus 2 to the third, that'll be 8 over 3. If I want to find a common denominator, I would need to, let's see, multiply by 3. So here I would have 12 over 3. Minus 8 over 3 gives me 4 over 3. So the area bound between my function f of x and the x-axis is given by 4/3. Now, I could think about this another way. It might feel silly to do this, but if I wanted to think about this as an area between curves problem, I can always find the area between two curves by integrating the two curves. I'm going to integrate over some interval a to b. I'm going to take my upper curve function minus my lower curve function, and hopefully that makes sense. If we were to draw this out, and let me see if I can find space. Let's just do that right here. I'll draw in what we're talking about. If I were to draw in, let's say here is my x-axis. Let's say here is my upper curve, and here the blue function, this will be my lower curve. When we integrate over, say, this interval right here, when we look at the definite integral from a to b of my upper curve with respect to x dx, that's going to give me all of this area underneath that black line, that black curved line. Which is great, but that's more than what I want. I want to take away this area right here. I only want the area that's between the black curve and the blue curve. So I need to take away that red shaded area, so I'm going to subtract the definite integral from a to b of whatever my lower curve is, because that's what gives me the area right here of this red shaded region. And then of course I can just combine those into a single definite integral, and it just makes the process look a little bit easier, a little bit nicer. So this is the process that we're going to use to find the area between two curves. We're going to take our upper curve minus our lower curve and then find the definite integral. So let's start here. I want to find the area bounded by f of x equals x squared plus 1 and y equals 0 for negative 1 is less than or equal to x is less than or equal to 3. So this piece right here, this inequality, is really giving us an interval. We're saying between negative 1 and 3. It's just a different way to write it. So I know that a is negative 1. I know that b is 3. I'm going to start by graphing this function. So here, let's see, x squared plus 1, negative 1 to positive 3. Let's see, my function right here, x squared plus 1. So let's see, here is what my function looks like. And already, I think we're going to have some oh, no, you know what? I drew negative x squared plus 1. I want positive x squared plus 1. There we go. That's a little bit better. Double check your graphs, ladies and gentlemen. So all right, I want the area bound by my function f of x and the x-axis between negative 1, so here's negative 1, to positive 3. I want to know what is this area right here. So in this case, it doesn't look like there's any intersections between my function and the x-axis, which is good. That works out well for me. So when I set this up, I'm going to set this up as the definite integral from negative 1 to positive 3. In this case, my upper curve, that is the parabola. That is x squared plus 1. So sometimes it'll help, I'll try and do this, to label your functions. This is x squared plus 1. So my upper function is x squared plus 1 minus my lower function. My lower function is just y equals 0. That's the x-axis. That's this piece right here, y equals 0. So I want to subtract 0, and then I'll integrate with respect to x. So I'm just trying to evaluate this definite integral. So if you can, first thing you'll want to do is simplify anything, combine like terms, distribute negative signs, things like that. Here we're just subtracting 0, so we can really just drop the 0. We can say the definite integral from negative 1 to 3 of x squared plus 1 dx. And we can just integrate this. So let's find our antiderivative. So our antiderivative, we should have x cubed over 3 plus x, and I'd like to evaluate that at 3 and negative 1. So let's see, I should have 3 to the third divided by 3 plus 3 minus negative 1 to the third over 3 plus negative 1. So let's see, 3 to the third over 3. 3 to the third would be 27. Divided by 3 there I have 9 plus 3 minus here negative 1 to the third will be still negative 1 over 3 plus negative 1. And then we're just simplifying this. So let's see, 9 plus 3, I've got 12. Minus here, negative 1 plus, or excuse me, negative 1/3 plus negative 1. I should have negative 4/3. So let's see if I wanted a common denominator. Well, first of all, let's do this. Minus negative plus a positive. 12 times 3, that would be 36 over 3 plus 4 over 3. The area bound by those two curves is 40 over 3. So here is the area bound by those two functions. So be careful here with these. You will definitely want to draw a picture of your two curves and kind of sketch in that area. Make sure you know exactly what area we are talking about here. This is probably the one instance I would say a graphing calculator would probably be helpful. If you want to use your graphing calculator to help you visualize these spaces, that's perfectly fine. But even if you don't have one, I think we can still get the general idea of these graphs across. Let's look at one more example for this video. Next up, I would like to find the area bounded by f of x equals 2x squared and g of x equals 4 minus 2x on the interval negative 2 is less than or equal to x is less than or equal to 1. So here the first thing I'm going to do is I'm going to graph this interval, graph these two functions. So we have 2x squared. I know that's a parabola centered at the origin that's opening upward. Oops. Let's make that a little bit better. And then g of x equals 4 minus 2x. I'm not going to get too specific here, but I know that the y-intercept is positive, so I'm going to go up 1, 2, 3, 4. And then I have a negative slope. So my function g of x, let's actually draw that in a different color. We'll draw that in blue. It's got to look something like this. So here this is g of x, and then this is, f of x. And we're looking for the region between negative 2 and positive 1. So I'm looking for, I would assume, this region right here. What is the area of this region? The one thing I am unsure of, and the one thing that makes me nervous, is this point of intersection. If they intersect somewhere in between this interval, if they intersect somewhere between negative 2 and positive 1, in that case, we would need to split this up into two separate integrals, because in that case, what the area would look like, I'm going to draw a different picture. In this case, my area bound between those two functions, I would have some of my area right here, but then I would also have some of my area right here, in which case my upper and my lower function flip. So I need to make sure that the intersection is either at 1 or outside of 1. So I'm just going to verify where f of x and g of x intersect. And the way I'm going to do that, I'm just going to take these two functions, set them equal to each other, and solve that equation. So I'm going to take 2x squared equals 4 minus 2x. This is a quadratic equation. The easiest way to solve a quadratic equation is to set it equal to 0. So 2x squared plus 2x minus 4 is equal to 0. Let's see here, I can factor out 2. That'll leave me with x squared plus x minus 2 is equal to 0. And let's see, this will leave me with 2 times x. Let's see, x plus 2 times x minus 1 equals 0, which will give me x equals negative 2 and x equals positive 1. And this is a huge relief for me. And actually, this tells me I'm going actually all the way to the left to that other point of intersection. That means that the points of intersection actually happen. This happens at x equals 2, and this occurs at x equals 1. And this is nice because it gives me this nice self-contained area. I have actually, those two are the endpoints of my interval. If I had had, say, x equals 1/2, or x equals 0, or x equals negative 1, some number that's between negative 2 and positive 1, then I would have some more work to do. But because they are the endpoints themselves, I'm not going to have any problems. So I'm going to set up my integral first. I want the definite integral from negative 2 to positive 1. And now I need to determine what is my upper function and what is my lower function. So look at this yellow shaded region that I've created right here. If you need to, draw a vertical line in there. Where does the top part of that vertical line hit? Well, that top part of the vertical line is hitting the blue function, g of x. So that means that g of x, that's actually my upper function. So this is my upper curve. And then down here, the parabola at this point right here, this is my lower curve on that region. So my upper curve is g of x. I'm going to have 4 minus 2x minus my lower curve, which is f of x, that is 2x squared dx. So this is the definite integral that I'm trying to evaluate from here on out. So let's see if we can do that. Here it doesn't really simplify to all that nicely. I will have, let's see, negative 2 to positive 1. I've got 4 minus 2x minus 2x squared dx. There's no like terms or anything that I can combine. So first thing I need to do, of course, is find my antiderivative. So I should have 4x minus x squared minus 2x to the third over 3. And I'd like to evaluate that at 1 and negative 2. So let's see, I have 4 times 1 minus 1 squared minus 2 times 1 to the third over 3 minus 4 times negative 2 minus negative 2 squared minus 2 times negative 2 to the third all over 3. So let's see if we can take our time here with this. I will have, and actually let's just do it right below, 4 minus 1 minus, this will be 2 over 3 minus, over here 4 times negative 2, I've got negative 8. Negative 2 squared, that'll give me minus a positive 4. Minus here 2, let's see, negative 2 to the third would be negative 8 times this. I'll actually have plus 16 over 3, excuse me. This would be negative 8 over 3 times negative 2. Yes, 16 over 3. So let's see. I'm going to simplify this a little bit at a time here. 4 minus 1, this is 3 minus 2/3. Minus over here, this is negative 12 plus 16 over 3. I'm just going to go ahead and distribute that minus sign through right now. So let's see, 3 plus 12, I've got 15, and negative 2/3 minus 16/3, I've got minus 18 over 3. So I have 15 minus 6, which gives me 9. So the area bound between those two functions is 9. So a lot of work, I think, went into setting this up. We had to make sure that we didn't have a point of intersection within our interval. That was the first thing that we did. Actually, excuse me, that was the second thing we did. The first thing that we did was actually graph the two functions together. So we graphed the two functions. We verified that the points of intersection were either on the endpoints like they are here, or if they're outside of that interval. If they're outside of negative 2 to positive 1, then we don't have anything to worry about. We set up our definite integral. We said here's our upper curve, that is g of x, that's the blue function, minus my lower function, 2x squared, which is the black function, the parabola. And then we just evaluated this definite integral. So there are a lot of steps to these, but once you get this problem set up, once we got to, say, this step right here, this should feel really, really familiar to the types of problems that we were doing in the last section. We should end up with just a definite integral that we should evaluate, and we know how to do that from the last section. So really the new ideas in this section are just setting up this definite integral, which will tell us the area between the two curves.